Okay, to wrap up this section, it's kind of a different little problem. It's called the birthday conundrum. All right, and it is kind of a fascinating thing to most people. I'm seeing some little boxes here. There was a translation error, I think, in my computer and my printer. Those little boxes should be times dots. Okay, so we'll fix that on this anyway. So we're going to look at this example. So in order for 4 people in a room to not have the same birthday, you take the number of days in a year. So the first person has 365 days to choose from. The second person has one less. The third person has one less than that. And the fourth person has one less than that. So the way this thing is set up in this numerator, that's a permutation, okay? This is where we have really independent events. This is an independent event. Okay, and notice, because we can write these in descending order as we did in the previous section. Okay, what about these denominators down here? Well, each one of these are individual fractions. So if you look at the numerator as a permutation, here you have 365 multiplied to itself 4 times. So your denominator is going to be this really nice large exponential number. Okay, so this is how you proceed if you're trying to get them to not have the same birthday, because this represents the number of days of the year that you're still allowed to hit after others are taken. Okay, so this means that the chances that 2 people or more of those 4 have the same birthday, this is that complement idea. This is no people. This is 2 people or more. So you think about this. At first I thought, where'd they get the 2? Well, 2 people have to have the same birthday. One having the same birthday with himself doesn't make sense. So this is 2 or more out of the 4 is a complement situation. So you'll say 1 minus that probability you have up here, and that will get the probability of at least 2 people out of 4 will have the same birthday. It's pretty small, but nonetheless. So let's do an example. These are examples that exactly follow the pattern. There's 2 problems in there. So in each one. In a room full of 10 people, what are the chances that none of them have the same birthday? Okay, so I'm going to put the probability that none have the same birthday is 365 days in a year, have a permutation of 10, and then we'll divide that by 365 raised to the 10. Okay, now I haven't calculated that out, but I will. Over here, what are the chances of at least 2 having the same birthday? Probability at least 2 with same birthday. Okay, so that's the complement. The complement of none is at least 1, or in this case, at least 2. If you have at least 2, the complement of that is none. So we're going to go 1 minus the probability of none, which is 1 minus 365 permutation 10 over 365 to the 10th power. So that is your setup. Okay, so let's see if we can calculate this one. I don't have it done already, so let's see what we've got. 365 permutation of 10, and then I'm going to divide that by 365 raised to the 10th power. Okay, so, well, that looks like a lot. If I just put those number. And then, oh, it's a lot because that's the probability of none having the same birthday. That's about 88% chance that they'll all have a different birthday. That makes sense to me. Okay, so if I take this and I just go 1 minus the previous answer that I got, then that's about 11.695%, okay, of at least 2 having the same birthday. Yeah, it could happen, okay. So let's just do the next one just so you have some examples. In a room full of 25 people, what are the chances that none of them have the same birthday? Well, there's none of them. Okay, none of the 25, so that's 365 days in a year. That stays fixed. Out of 25 people, we're going to make that a permutation, okay? Because once somebody claims a year, remember, or a day, then the next person can't claim that day. And this is to the 25th power. So when I crunched the numbers on that, I got 0.4313. And then when I had the probability of at least 2 with the same birthday, so I'm just going to say 1 minus, and then I'll just subtract that decimal. The setup, though, should look like this. It's always good to practice form, because the more you write it, the more you're likely to remember it, which is 1 minus 0.4313. And I got 0.568699704. Okay, I had a lot more decimal places there to make that happen. So notice that as your number of people in the room increase, the chances that none of them will have the same birthday goes down to about half what it was in the previous. And then the fact that at least 2 have the same is a little bit, it's about 56, 57%. That at least 2 will have the same birthday. All right, let's just finish up with this last one. In a room full of 50 people, okay, the probability of none having the same birthday is that same 365, permutation of 50, okay, and then that's 365 to the 50th power. Sometimes I keep thinking, when is this going to overload my calculator? But so far, hasn't. 2 with same birthday. So that's 1 minus 365. And it looks like that. So I didn't crunch those, so I will use this calculator to make that one happen. Just to give equal work here. 365 permutation of 50 divided by 365 raised to the 50th power. Uh-oh. It overflowed that one. Let's see if it'll overflow this one. Okay. 365 permutation 50. It kind of makes sense because the number of permutations is going to be a whole lot larger than the number of combinations. Whoa, we got an overflow there as well. So what do? Well, if you have an overflow, then I am perfectly content for you to leave this answer, and I'm perfectly content for you to leave that answer. I don't think it's probably, we could play with the numbers and we could, decrease that down to where we could do the calculation, but I'm really just pretty happy with here. So that is applications of counting using the idea of probability.